Step into any cafe on a quiet morning. Phone lights up, emails flutter in, yet no wire touches the glass. An unseen something, call it a whisper in space, has reached across the room, carrying every word you will read. That whisper is an electromagnetic field. A gentle oscillation of electric and magnetic influence filling the air like an inaudible song. Not far away, an MRI scanner hums in a hospital basement. It persuades the tiny magnets inside human atoms to sing back detailed portraits of beating hearts and resting minds. Those images, too, are the handiwork of a field, radio waves coaxing nuclei to dance in precise rhythm. Now stretch your imagination a little further, to the detector halls beneath the Alps, where protons collide at nearly the speed of light. Out of the debris, physicists have glimpsed ripples in yet another field, a pervasive ocean called the Higgs. Unlike Wi-Fi, it cannot be switched off. It is everywhere, right now, pressing gently on every electron and quark, giving them the resistance to acceleration we experience as mass. If the electromagnetic field hands you emails, the Higgs field hands you weight. What, then, is a field? Picture the surface of a lake at dawn. Toss a pebble, and concentric waves spread outward. You do not create water itself. You disturb what is already there. In modern physics, every particle is just such a disturbance. A photon is a brief ripple of the electromagnetic lake. An electron, a more intricate swirl in its own dedicated pond. Even the warmth in your coffee is the combined jiggle of countless invisible waves. We were not always so wave-minded. For centuries, natural philosophers spoke of tiny billiard ball atoms bumping through emptiness. The shift from hard particles to soft fields is one of science's quiet revolutions. No banner moment, but a gradual realization that what we call objects are really packets of energy moving through continuous, layered media. Rocks feel solid because their waves lock together in tight patterns. Light feels intangible because its ripples glide through us with effortless grace. More astonishing still, the so-called vacuum, the space between stars, refuses to sit silent. Even stripped of matter and heat, it trembles with residual motion. Field lines flicker. Pairs of particles appear and vanish. A restlessness that underwrites lasers, superconductors, perhaps the birth of the cosmos itself. Over the next hour, we will tune our senses to these hidden symphonies. We'll see how field theory powers every text message, every fluorescent bulb, every GPS fix. We'll wander into the LHC's subatomic surf to meet the Higgs. We'll dive into graphene sheets, where electrons forget their mass and skate like light, and we'll ask a final daring question. Could space-time, the very arena of distance and duration, be one more field among many, rippling with our every step? Prepare to trade the comfort of objects for the elegance of waves. The universe is humming all around you. All you need to do is listen. Hold a compass flat upon your palm. The needle trembles, steadies, and points always to some far-off Arctic emptiness. No wind pushes it, no string pulls it. Instead, an unseen pattern threads the air, whispering directions to iron the way a conductor cues violins. We call that pattern a magnetic field. At every point in the room, there is a tiny arrow, too small to see, nudging anything with north-seeking courage. Slip the compass away and flick a wall switch. Filaments glow, street lamps ignite, whole cities pulse awake. Here another pattern takes charge in electric field, urging charges along copper veins. Lighting tungsten, brewing morning coffee, remove the wire and nothing flows. Reconnect, and the push resumes as faithful as tide and moon. These examples share a quiet truth. Space is not an empty stage where forces hurl objects like props. Space itself carries the instructions. A field is simply a map that tells everything, everywhere, how to move or turn. We do not glimpse the map directly. We infer it from what it makes matter do. The compass pointing, the lamp shining. Imagine, then, every square centimeter around you filled with overlapping lattice. Magnetic guides, electric prods, gravity's gentle downward pull. The world feels solid and separate, yet beneath it lies a mesh of influence, invisible but pervasive. Hidden geometry that shapes every gesture and glow. Now close your eyes and listen to a cello. Low notes stroke the room, high notes pirouette past your ears. Nothing solid crosses the gap between string and skin. Instead, the cello nudges the air itself, compressing and stretching it in rhythmic wrinkles we call sound waves. In one moment, the air molecules crowd together. A heartbeat later, they drift apart, peaks and valleys racing outward at the speed of a gentle breeze. To picture this, drop a pebble into a still pond. Rings ripple away, but the water molecules mostly bob in place. It is the pattern, the information of up, then down that travels. Sound behaves the same, only the pond is invisible and three-dimensional, filling theater halls and forest clearings alike. Every wave owns two simple traits. Wavelength is the distance from crest to crest, the span between one push and the next. Amplitude is the height of the push, whisper, quiet, or thunder loud. No formulas are needed. Stretch the wavelength, and you hear a deeper pitch. Boost the amplitude, and the volume swells. These ripples in air remind us that fields are not exotic abstractions reserved for physicists. They are the most ordinary companions. Breath that carries speech. The bass that rattles windows. The crack of thunder announcing a summer storm. By starting with waves we can feel, we prepare to meet waves we cannot. Ripples of light, of matter, even of the fabric of space itself. Those lie ahead, waiting just beyond the next page of our cosmic field guide. Mid-Victorian Britain was a world of steam whistles and telegraph clicks. But in one quiet study at King's College, James Clerk Maxwell saw farther than rails and wires. On his desk lay two puzzles. Sparks leapt between charged objects, and magnets tugged iron filings into graceful loops. Most scientists treated these as separate tricks. Maxwell asked a bolder question. What if the electric push and the magnetic swirl are two faces of one deeper dance? Working with little more than ink, paper, and a mind-tuned to symmetry, he found the answer. A changing electric field creates a magnetic field, and a changing magnetic field creates an electric one. Set either one in motion, and they chase each other through space, leapfrogging forever, a self-sustaining ripple. His equations predicted a speed 300,000 kilometers per second, and, when he checked, it matched the measured speed of light. Sunlight, candlelight, the glow of distant nebulae, all are electromagnetic waves. In that stroke, Maxwell united optics with electricity and magnetism and offered humanity a new superpower, the ability to launch controlled ripples across empty air. Within a generation, Marconi would send Morse dots over the Atlantic. And a century later, Wi-Fi routers would beam cat videos through apartment walls. Yet every radio call and laser pulse, no matter how playful the content, still obeys the elegant choreography penned by Maxwell's hand. Fields, birthing fields. Light as the grandchild of an invisible marriage. Imagine dawn in a city apartment. A smart speaker requests the morning playlist. Halfway across the room, your phone obliges, though no cable links the two. The speaker's antenna shakes the electromagnetic field in rhythmic patterns, 2.4 billion ripples each second. Those ripples spread, weaken with distance like the glow of a flashlight, and arrive at the tiny receiver in your palm. The phone circuitry translates field wiggles into pulses of current, pulses into bits, bits into Bach, or Beyoncé. Step into the kitchen, pop a bowl of yesterday's pasta into the microwave oven, and another field trick unfolds. A magnetron inside the metal box squirts out waves just the right wavelength, about 12 centimeters to set water molecules spinning. Friction at the molecular scale becomes warmth at the plate. The oven cavity is sized so waves bounce back and forth, piling atop one another into standing crests, hot spots that cook food from within. You're harnessing Maxwell's waves in a corrugated metal cave. Even a simple coaxial cable, the fat cord feeding your router, acts as a waveguide, corralling electromagnetic ripples the way copper pipes steer tap water. Strip the cable's shield, and the signal fizzles, leaking strength into the air. Perhaps you've noticed that signal bars improve when you raise your phone near a window or shift your body. Your flesh, rich with salt water, absorbs microwaves and glass lets them sail through. In daily gestures, without equations or lab coats, we all negotiate with fields, seeking the clearest path for waves that whisper news. Laughter, alarms, and lullabies across the ordinary air we breathe. Fields, like rivers, can be steered. Peer inside a cut-open coaxial cable. A copper rod runs through a hollow shield, separated by plastic foam. When radio waves flow down this corridor, their electric part hugs the center, their magnetic part loops the walls. Perfect balance, none spilled. It is plumbing for light, coiling through walls to a rooftop dish. Scale that corridor up, and you have a waveguide. Silvery pipes that carry radar pulses to an airport antenna, or channel microwaves through a magnetron's copper maze. Inside, the waves ricochet, forbidden to leak because metal walls force electric fields to zero. It is as if the pipe whispers, this way only. Sometimes, though, we want silence. Step into a Faraday cage, an elevator, perhaps, or a mesh room in a science museum. Your phone's bars topple, radio vanishes. Lightning outside cannot touch the notes of a delicate instrument within. The cage's metal skin herds currents that cancel incoming fields, much like noise-canceling headphones, but for space itself. You've practiced small-scale fieldcraft without noticing. Tilting a handset, raising it near glass, shifting to an open doorway. Your body, bags of salty water, soaks up microwaves, creating literal dead zones. A half-meter pivot can rescue the signal, letting waves slip past ribs and shoulder into the waiting antenna. Guiding, blocking, amplifying our species has learnt to fence with invisible lines. Turning an abstract lattice into highways, vaults, and whispers that crisscross daily life. Up to this point, waves appear tame. Brighten the bulb, grow the ripple, dim it, and energy wanes smoothly to nothing. But nature harbors a kink in that logic. One revealed with a simple slab of metal and a beam of violet light. Shine a dim gray lamp upon a zinc plate and nothing happens. Increase the brightness, and still the metal refuses to budge. Swap the lamp for a faint, ultraviolet glow, and ping. Electrons leap free like popcorn. No matter how weak the UV beam, each electron emerges with the same kick, as though light arrives not in sliding volumes, but in indivisible parcels. This is the photoelectric effect, and it shattered the classical picture. Light's field, it seems, is not infinitely divisible. It comes in quanta, photons whose energy depends on color alone. Brightness merely counts how many photons knock in quick succession, not how forceful each one is. The revelation opened floodgates. Lasers that weld steel yet carry music down optical fibers, solar panels that swap sunlight for charge, night vision goggles coaxing photons from a dim horizon. All exploit the fact that fields, when pressed to their smallest scale, reveal a grainy texture. So we arrive at a threshold. Classical waves guide compasses, songs, and Wi-Fi, but cannot explain why blue light frees electrons while red, however intense, does not. To continue, we must venture into a quantum landscape where every field wears two faces, smooth ripple, and countable spark. In the next part of our journey, we'll meet those sparks and see how particles emerge from the restless seas that truly compose the world.